Okay, so welcome everybody. So let's start the second session this morning. So we are very happy to have Professor Jaejun Yu from Seoul National University, Korea, and Professor Yu obtained his PhD in 1988 from Northwestern universities in the U.S. Then he spent some more time in the U.S. as a research associate. In 1992, he went back to Korea and became an assistant professor at Sogan University. Is the pronunciation correct?
Yes.
Sogan, okay. And since 1999, he has been a faculty member of Seoul National University. And Professor Yu is an expert in theoretical and computational condensed matter physics with a particular emphasis on the physical properties of transition metal oxides and derived materials. And personally, I first met him in 2017 in Daejeon, Korea, when we attended a small workshop about graph bands, and he was really impressive because he kept asking very critical questions to almost all the speakers. So today he's going to tell us about linearization and identification of topological phases. So let's look forward to his talk. Okay.
Thank you very much for the introduction, Professor. And also I'd like to thank you, Professor Dasuta, and also for the organization of this wonderful school and workshop. It's really a pleasure to come in here after this long COVID block. And we couldn't meet each other. Actually, we're having a long history of having Indian Korean joint symposium, but for the last 2 years we are just able to see only over this the virtual meeting. So I'm very glad to be here, and also I'm very glad to see many young physicists and scientists here. So and also it's good to have a chance to give a kind of lecture. In fact, I was told that I have to give very pedagogical and or something very easy to understand what's going on with topology and solid state physics. So, but the thing is, this topic is not so simple, and why this got flicking over here. Yeah.
Yes,
Why so slow? I mean, the Wi-Fi is not. Shall I change to something else? Oh, okay, yeah. Now it's sorry, maybe the Wi-Fi that I connected was a bit slow and didn't make it. So I plan to have to divide this topic into lectures. One is lecture on some general ideas and topology. Then, and the second lecture will go a little deeper and how we really do the calculation and what types of topological invariants that we are talking about. So I think I gave this reference to the organizer earlier, and most of the basic idea was actually from Professor Resta's lecture notes. I think it's coming in a book saying geometry and topology and electronic structure theory. It's a very good one to go over to get the general idea and how we approach this topology in electronic structure theory. And more practical one is on by Professor Van der Wits on the Berry phase, the calculation of this Berry phase in many of the solid state systems, including topological isolations. and real practical matter. In fact, when I started to do this some time ago, I get into this paper by Professor Fukui and Katsugai and Suzuki, that how we do this on discrete Lagrangian and do the real calculation. And more updated version of that actually came out with by Bright and co-workers. And also there are some of the tools available in Vanier.org. And also there is also one by Vanier.org too. So there are some practicals. I think that maybe students will go through some of those later for the test. So let's get into some basic ideas. So I'll organize the thing in this order. So first we'll talk about some really general concepts of geometric phase in physics. And then we move to how this Berry phase is connected to the geometric phase in quantum mechanics. Well, actually, simply in U1 gauge theorem, that's just this phase in complex numbers. So that's how it is connected to the geometry and quantum mechanics, and we'll figure out how this Berry phase and the Blow state, that is the eigenstate of the Schrödinger's equation in periodic solids, so that how those two are related, and then consequently we'll talk about some of the quantum Hall effect in solid, or some unquantized version of this quantum Hall, which is anomalous Hall effect, and also we see some other cases of this magnets. Then we'll summarize some of the topological invariants that we're going to discuss, and but in the meantime, we will get back and forth and some of the ideas how this Blow state is connected to Vanier function, which is the core of our discussion. So, this is an article in 1990, some general ones. I was amused by this idea. In fact, when I was young, and I was curious that when you throw cat over the window, and whatever you do, initial oops. Shall I change the Wi-Fi again?
Everybody switch off their Wi-Fi, please.
Okay, yeah. Well, I will stay on and see. If it's not working, I will switch to different. Yeah. So. Okay, yeah, this is also topological too, but somehow we are entangled. But the thing is, when the cat's supposed to drop on his or her back, but finally she lands on foot, regardless of its initial position. That's very amusing, and the thing is, if you think about this is a typical argument when we in the general physics course, that the angular momentum should be conserved, and you cannot make a rotation without any torque acting on her body somehow. But the thing is, this is not a rigid body, but it has lots of degrees of freedom inside, which the coordinate of which we don't know. So by coming down and falling on the floor, it's making some internal rotation or something. So that can adjust the cat can adjust its body somehow that they land on foot. safely. So this is just some of the counterintuitive to what we know as rigid body rotation. So it means that what we have to do is that we have to consider some internal degrees of freedom, which actually counterfeit what we think as a single degrees of freedom of angular momentum conservation. So another example of that is so-called parallel transport. So this is like Foucault's pendulum problem, that we start from the North Pole and we move. This is we're not really rotating or whatever anything, but thing is on the Earth's surface is just round. It's a sphere. So if you move your pendulum, which is like clicking like this, but they go on one direction like that, and without any rotation, you just move along the equator, and you go back. Then you came back to the same position, but at the end, the angle of this the pendulum is actually rotated by the solid angle it has traveled. But there is no direct rotation of this the pendulum swing. But at the end, actually, it has changed. So this thing is also kind of what they call as NA's angle, but I don't know about this terminology, but you will understand the physics. So you make a parallel transport, which doesn't mean that you are actually rotating local frame, but still at the end you end up having different endpoints. That's what we call the anholonomy. That we are actually following some path continuously from one point to the other, but at the end you end up in a different position, something like that. So the similar thing happens with this the basic quantum mechanics, the interference phenomena, so-called Aronoff-Bohm effect. So when these double slit problems, that electrons actually pass through these holes and they actually interfere. But this interference under this red box is actually understood by a different traveling path of electrons through one slit over the other. So the whole thing can be drawn as a bigger picture. So you have the one traveling path like that, and another one going like this, and the difference can be calculated by this sum of this phase change via this vector potential A between the path gamma 1 and gamma 2. So it's like making a closed circle like this. But once you have some other external flux going through this path, but not actually interfering any of the electrons traveling in the ON. So the flux will be, the magnetic field will be confined within this circle, but the vector potential which actually extends far further and creates a different change of this electronic phase. So that actually causes interference, and this one can be seen just by this the interference effect, what we call in quantum mechanics. But this phase, the vector potential A, or this geometric the magnetic field or flux coming through this one, can be interpreted also as a geometric meaning. So they are somehow connected. Another extreme one is we know that although it's not realistic yet, it's not found, but suppose we have a magnetic monopole in the universe, and then we should have some singularity at some point, and creating some string of lines, singularity lines. But suppose we have some singularity somewhere here within this sphere, then we got to have some of the flux which it should naturally come out and connected with all of it. So that is actually a natural way of we are making this magnetic flux by some singularity exists in the system. So it seems it's all separate, but somehow they are connected. So when you talk about some of the geometric phase, which we're going to discuss as a Berry phase later on, can be realized in many different ways. So basically, what we deal in quantum mechanics is the phase of the wave function plus the amplitude of the wave function. But this phase is actually playing a quite important role in many ways. So one of the examples is a superconductor with magnetic flux. Okay, so we all know this in terms of Ginzburg-Landau theory that we can write this quantum mechanical wave function as an amplitude time it's e to the I pi, which represents the phase of that wave function because it's a complex number, and this phase is natural that we divide by the amplitude and phase. But this phase is also interpreted as an angle in complex plane, just like here, what I showed on the picture. So this chi is literally the angle of this rod relative to the x-axis. So that's what meaning of this debate. Now, since in quantum mechanics, this is so-called U1 gauge, and gauge degree of freedom, so-called gauge theory, we have it naturally couples with some the vector potential. In fact, well, there are many different ways of interpreting this, but I'll come back to this point later at the end. But anyway, so when we say this the vector potential, which is supposed to be related to the magnetic field, but in fact, in superconductor, this is a direct the direct consequences of this vector potential A is the current itself. So this vector potential is proportional to J. That's a London equation that we all know about. But at some point, even without any magnetic field giving out to the vector potential, that means without if A is 0, then just the simple gradients of this phase chi can induce a linear current. That's what we call a supercurrent. So if it's in the linear dimension along the x, so one end of the superconductor has a phase chi 0, and the other side you have a chi 1, then the gradients created by these two different phases will lead to a supercurrent system. But a more interesting setting can be found by just wrapping up this one-dimensional superconductor into a circle. So then we assume that this chi along this the boundary of the superconductor is very well. I take this r to the infinity, but suppose we have a macroscopic size of the superconductor, and the boundary condition at the end of the superconductor is proportional to chi. That's just a rotation of this angle along the edge. That means because this direction change is also caused the gradient, which is along the direction of theta. That's the direction of the angle. So it's natural to have currents going around these boundaries of superconductor. In fact, that is nothing but this precursor vortex, which has a supercurrent circling around. So since our current is flowing around it, and you got to have some magnetic flux focused at the center, which has to be singular because it can't be multi-valued function. The theta varies all the way in all directions, but it cannot have multi-value at the center. You only to resolve the conflict is to have 0 amplitude, means that your superconductivity is broken at the center. So that's what makes this so-called the vortex, and that's realized in reality, and we have the superconducting density is actually vanishes at the center, and at the same time this the variation of the phase, which can be converted into a vector potential. In fact, it has to compensate the change of the phase of a superconducting wave function by the presence of this vector potential that makes the rotation of this frame. Anyway, that leads to this configuration that any singularity you have within the superconductor is actually associated with this magnetic flux around it, and that's the reason why we have this type 2 superconductor type. So in physics, we have lots of ways to see how this the phase of the wave function is connected to the physical phenomena, especially on superconductor. But it was not long ago that we realized that there is more on our more in the structure of this the wave function that we deal with in solid state physics. So I mentioned about this Foucault pendulum moving from North Pole to equator and going around and circles the position back. And that's what we call a parallel transport. In that case, we have suppose we have some vector pointing to some direction. So we suppose that that's the then we need a two frame E1 and E2. So this is a two-dimensional circle that we described. So any angle between this E1 and any vector so can be described by this frame. But the space, the geometrical space that it is embedded is not flat. That means if this is flat, then wherever you move, the E1 and E2 may not change. But if you are in the curved space or somehow, then although you think you are moving straight like this, but you are actually moving like that. But the angle between the two is always orthogonal. But you never know that whether you move somehow, you're rotated by this much, but it's not perceivable. So so-called kind of this parallel transport is so-called kind of adiabatic transformation of this coordinate on different positions in space. So while we're moving this E1 and E2 with respect to some angle, the rotation axis omega, and by the amount of the rotation velocity omega, the vector, then still at some point you are actually trace it down. But at each point of the rotation, you must obtain this relations that they remain orthogonal in any way. So if you write something as any complex wave function, in this case by just the rotation, the angle, the basis function of that in complex space, then you can actually represent this two vector with this complex coefficients. So time of evolution of this one, which is actually related to the rotation of basis E1 and E2 by this way. So that's somehow we can actually trace that. But this can be actually translated into in terms of wave function. So instead of writing this as the mathematical two-dimensional vector, we can actually write this one in the form of the wave function that we deal with. And the alpha of x is actually the angle of rotation of this E1, E2 relative to the original, the fixed frame, the x-axis. So as the angle alpha changes, then this frame is actually rotating like that, and that can be represented by this wave function on this side. So this is what we are natural. Everybody here who knows the quantum mechanics be very familiar with this expression, where this alpha by the phase that we usually referring is actually represent the angle of rotation of this frame at each point. So we are now making a kind of geometric interpretation of the quantum mechanical phase that we have. That means it's the angle of rotation of this frame. So then by the simple mathematics, you can see that the change of this wave function that actually includes both the change of the amplitude over here or the change of the angle that we see. So there's two, but if you just take this imaginary part of it, then that is actually enough to take into account the change of the angle all of this closed loop that we can actually represent like that. And this is like a Stokes theorem that we can change this line integral to some of the surface integral, where this term, this big, this sort of a cross product of dx1, dx2, and so on, can be interpreted as kind of by some flux that we will discuss later. So the major point of that I stress here is that any phase factor that we deal with in the quantum mechanical wave function can be interpreted by some of the angle of rotation, so on. So that's some new point that I like to stress. But now coming back to this quantum mechanics itself. So let's say that this is called adiabatic theorem. This is nothing but just we make a small time-dependent perturbation. But if the perturbation is so small and the level splitting of the energy level between the quantum states are big enough so that a small change of this time-dependent perturbation do not make any meaningful transition between the two. In such case, then we can actually solve this one in a sort of interaction picture that is a combination of normal time evolution of this basis set times the phase factor that we're going to deal with, which is actually just simple evolution by the energy, but also there is an additional factor of this coefficient that comes with this term. This is actually very tricky one. So this one will make up with this additional time evolution other than the normal energy evolution. So the adiabatic theorem is that in the course of this time-dependent perturbation, we have a block of energy levels that they make some time evolution, but the state belong to this block will not make any transition outside of that block. So that means that this block of energy state, which we call as the bands, the block manifolds of bands that remain as a unitary throughout any time evolution by the time-dependent perturbation. So if this adiabatic theorem holds, then any quantum mechanical wave function, the time evolution of wave function with some time-dependent perturbation will end up by having this this psi n and the bracket of psi m and n, the time derivative of the end state, and that actually come up with this this simple, the first of the differential equation. In fact, this is not just simple, but it is a kind of a matrix equation at the end. Anyway, so we'll have this coefficient m can be integrated, and we'll end up having some phase. So we're not actually giving out any amplitude from the m manifold to the outside. Then everything will be captured by this phase vector. That's what we call as the Berry phase. But what this is so far is very abstract, but we'll come back to this point as we go on. So, so just summarize what I have described. So we started with some geometric picture of how things works, but we came down to all of this geometric picture into the phase of the wave function, and that phase, in fact, can be divided into two types of thing. One is so-called fast variable. What we can say this is like an electron coordinates, and also slow variable, which we can say it's related to ions, the atoms, which is a heavy object in solid state. So the motion of ion or atom is slow, but electrons move very fast. So if any of the systems that we describe, together by the change in position of atoms or ion and the electrons, then the quantum mechanical wave function of the electron can actually gain this extra phase other than this time evolution by the energy, which is actually changing adiabatically, depending on the position of ion. But we gain another extra term other than this time very fast oscillating energy term, that this term actually belongs to the Berry phase. That's what is defined in his original paper. And then how we calculate this gamma, and that actually is simple, very as simple as this. So if we have any diagonal components of quantum state n, is the n, the same n as this one, and then we have a scalar product of n with time derivative of n, and that actually builds up with this gamma. Sorry, we need something here. So we take the integral of that along the path of this motion of r, and that can be interpreted by this term, with not because initially it's a derivative with respect to time, but it's a derivative with respect to the slow variable and gradients r. So that can be considered as a vector potential, and that we call as a Berry connection between two different state n with different r, in fact. And then this, once you have a vector potential, then we can apply for the same the math that we use for electrodynamics. That by taking curl of A, we get magnetic field. Here we get so-called Berry curvature. So this is the whole structure that we are going to deal with. I went through this very fast, but since I'm going to reiterate, so if you have any question coming up, then you can interrupt me anytime. Yeah.
Could you go back to the previous slide?
Yeah. This one? Or?
Yeah. So is the second last equation correct? I mean, Cm dot T equal, the next one.
This one. Oh, sorry. So you're talking about this, the index.
No. I mean, the left-hand side is time derivative of Cm of T, right?
Yeah. Yeah. So this is the first of the ordinary difference equation.
Yeah.
So C dot is the same as minus this term times Cm. So this is simple, the first of the differential equation. Yeah, actually I mixed up with this, there's it has to be this dimension, but sorry, I think I just mixed up with this this one's supposed to be n because, and with different n, normally it just goes off as an orthogonal. But yeah, I'm a little bit rough on this, but yes, we can come back to that.
Thank you.
Any question on this very general formula? But this is any textbook just deal with this, so you can actually come back and see it. So question is to understand, how these things it really happens with. If you just look at this term, this formula like this, it's very hard, really difficult to capture, what Berry phase really do. In fact, when this was proposed quite a while ago, but
Jaejun, what is the integrand here? I mean, psi t.
Which one?
Psi t of written, right, as an integral. So E n or what? Yeah.
This one. This is the energy of n state.
Okay.
But since this is a slow variable, if you solve the Schrödinger equations for given r and p, then the energy eigenvalues of that will depends on the position of the atom at that time.
Okay.
This is very just simple, quantum mechanics with atoms and molecules with different positions of atoms. So suppose my hand is the position of atom, so you can solve like H2 molecule with distance like that and distance like this. You will have a adiabatic change of your quantum level just going, like they just split it like that. But each one of that, as this move along, have different energy because they have a small overlap, so it's almost the degenerate two state. But if you come closer, then you have a bonding and anti-bonding. But they make a transition from here to here. So you have a bonding state of energy, which is actually a function of R, right? Okay, so it's very simple quantum mechanics. So you move along the atom like this, then your energy level changes. But the evolution of that for given R should be a time evolution of like this. But the point is that so this is like a kind of fast oscillation of the energy of the phase rotation of energy like this. So from later on, we will actually try to get rid of this fast oscillating thing, and we just want to deal with the some key idea is that if you deal with this kind of slow variable and fast variable stuff, then by the change of this R, there is actually net additional phase is acquired by the change of this position of slow atom position. So the thing is how we identify that one. So people would say, okay, but this is still just the phase in front of your global phase in front of your wave function. So what would it matter? In fact, but the thing is, actually, it is. The thing is, you actually start from this one, and you come closer. Then you just change the position and go back to the original one. Then you end up to the same position, but you will get a different phase like that, which can be can cause some kind of interference or some kind of quantization, whatever, which make this system as non-trivial. So the earlier example of this Berry phase, which was not in solid state physics, in fact, people didn't realize that this types of non-trivial structure happens in K-space. But originally, people figured this on the molecule, like the methyl or methyl at the molecule. That you have one nitrogen with three hydrogen around. Then now you move your nitrogen going through this three triangle of this position of hydrogen to the other end, but you end up to the same molecule, but with two different positions. So it's like a Mexican head type potential you get. But this one actually you can get this one going through the middle of it, but also you can rotate it like that, and you can come back to the same position. So there are lots of ways to manipulate the molecules in different position of moving this R. So at the end, people find that there is some role of this extra phase, but which was not actually exciting as it is now. But
so you are calculating the time evolution of the fast variables, right?
no,
Psi t.
This one.
Psi t is equal to this time evolution of nr.
Yes.
What is psi t? Is the time evolution of the
This one, you mean?
left?
Oh, this one.
Right.
Yeah, this is just the time evolution of the whole thing. Yes.
Whole thing.
Yeah.
With the frozen ionic positions, right? Or
Right. Forgiven. No, actually, this is varying in time.
okay.
So this is
So psi is a function of RP capital R capital P.
yes.
And T.
Yeah. Yes. It has all the.
Okay, good. Yeah.
No, it doesn't have small r and small p, but it's a capital R and capital P is here.
So this is the time evolution of the slow variables.
Sure. Yeah.
Okay. And then what is your n when you compute the phase?
Which one? This one?
No, next line.
Oh.
So you want n dot, right?
This one, yes.
So what is that n dot?
So this one will evolve from, this is the basis. Well, you choose one basis, initial position, the initial state of that, then this will evolve in time.
Okay.
The same as this time here is same as our rotating frame. So initially it was like that with alpha fixed, but in a little later time it will rotate like this. Then the original wave function and the rotated wave function will have a product. That one, yeah. That's the one. The change of the rotating frame is counted over here. So we'll come. Yeah. So this concept will become clear if you see that how it is actually mapped onto the case-based physics that we talk about. But now, but this is even in a single particle stage, it's very dramatic. In the beginning, I mentioned that this magnetic monopole we have is something singular in space, right? But that can be realized in a simple way as this one. So let's say, consider you have a classical rod of magnet. This is sort of solenoid. If you have a magnetic, it's the solenoid like that. And then the magnetic field actually flux is going like this. Of course, it goes come back here, but this has a uniform magnetic field within this solenoid, and you have like one quantum spin sitting at the center, which is a quantum mechanical object. But the solenoid itself is a classical object. You can control the direction, as you just move by hand, right? So then the thing is, so this solenoid, direction of this solenoid is characterized by B. That's the direction of the magnetic field going through this solenoid, okay? So the position of this, the direction of this magnetic field is a classical variable or flow variable that we are going to move around this by hands or whatever. But the quantum state sitting at the center is spin half object that couples with this magnetic field. So this is a quantum object that we deal with. And B is the classical magnetic field that we can control, or it's flow varying. So then when this direction of this magnetic field or solenoid, the direction is like characterized by theta and phi in polar coordinate, then this Hamiltonian, we can write it down and find the eigenvalue like this. This is very simple. Now, this is exactly what we like to do. So, following the idea that we described below. Okay, yeah, well, it has a very long, yes, delay. Okay, I have to finish explaining if we come back. So now we define this n, this quantum state, n is a spin up or down. Okay. Now that actually depends on r, which is theta and phi of this direction of solenoid. You got it? And so if you take the derivative of this theta and phi, then you can calculate the gradients of this quantum spin states rotating with respect to the solenoid. Okay. It's taking too long. Okay, so now come back. So this state is eigenstate of that, either plus up spin or down spin, but still it's a function of theta and phi. So we take the derivative of gradients of that r means you take the vector direction pointing theta direction or phi direction. So you can calculate this and construct this vector potential A out of it. That's exactly something like this. And if you take curl of A, then that's a flux. This is a Berry curvature, which corresponds to this virtual flux coming. It comes like that, but it's very interesting that once you do this, then you're getting something of 1 over B squared. The B is magnetic flux. If B goes to 0, then something happens singular, right? So it's exactly if you take this types of thing, and you reduce the magnetic field solenoid, the magnetic field in the solenoid to 0 and small and small and small, then you're getting actually extremely strong flux coming from that source. So this is exactly what you see in monopole. I should go back, but I'm afraid it will take a long time to come back. So you should imagine from your head how it happens. But then I think you'll be amazed by exactly same thing happens with this direct current physics that you always deal with for these days. Not everybody, but anybody who works with graphene or whatever in topological material, then you see why people are so anxious about to see this direct current in the electronic structure. So here is now the direct current is a simple band structure like that, but it's not usual as to see this types of structure in K-space. But the K-space that we deal with in the Bernoulli zone is it's not the dynamical parameter. It's something that we can set by the symmetry of the system, by the translation properties. So if you have some electronic state, by moving by the translation of crystal momentum of K, and then you can define a state like that. But so if you see any of this band structure like that with your center shifted to 0, then you can write your Hamiltonian as a function of K, which we can control. Let's say, not exactly, but yeah, it's a kind of parameter that we deal with. Then you say you have one spin. It can be real spin or pseudo spin, just like in graphene. You have a orbital basis, degrees of freedom. Then you end up exactly the same expression as I said. Okay. Yep.
K is a slow variable here, right?
Pardon me?
K.
K is what do you mean by low?
Slow variable.
Slow variable, yes.
Why?
Yes.
Why?
Why? No, it's not just slow. It can be just static parameter. You can actually drag it. You can change by hands. For example, you can choose K. Right? When you draw the band structure as a function of momentum K, that's a crystal momentum, not the real dynamical momentum. I'll come back to that Prof theorem at just next page. So we'll come back to that. But this is just the expression that so we understood that by handling quantum spin within this classical solenoid, you just rotate like that, and by controlling the magnetic field, you can come to the point that where the magnetic monopole exists. And the same thing is true over here. And mathematically, it's exactly the same. And K goes to 0 means right here, at the center of your direct current, it is singular. And well, it's not real magnetic field, but it's a kind of fictitious magnetic field in K space that you have a very singular value of magnetic flux going out of this magnetic monopole which exists in direct current. So you can actually say, okay, there is something, and topologically non-trivial. And of course, this flux can be calculated by this omega c, which is actually by the solid angle. Omega is a solid angle. So if this exists within this three-dimensional space, then you make a solid angle by putting some sphere surrounding that singular point. It's just 4 pi. That's a direct magnetic monopole you have. So what I said so far is a very simple arguments that how this slow variable and fast variable, but this is all already very familiar, but that the same structure actually exists there. So we can explore how those exact same the singular points actually carries around whatever K-space structure we get in real solids. Okay. Any questions? So well, this is very simple analogy that. By the way, how am I doing my time? 25 minutes, okay. So yeah, so I think that this one actually, I thought this is an essence of whole thing that I'm going to talk. And now I can move a little faster. You know, how we construct this, the case-based business that we just described. So since just the elementary solid state physics course, you hear about growth state, but that actually depends on some system with this T. T is a translation operator acting on a function f of x, which means that we are moving this function by distance a, which is the subscript of this translation operator. So any Hamiltonian, we express it in real coordinate x, then in theoretic system, it's just like this. If you put all the same atoms, every distance of a, then they have a translation symmetry of by a. So the Hamiltonian of x at position x is exactly the same as by the system we translate by a. So in terms of operator, we can say this Hamiltonian and translation operator commute. So if you take this, if you solve this Hamiltonian, then you get some eigenstate. This is we're solving this theoretic Hamiltonian, and you get some eigenstate like psi k, and the eigenvalue of epsilon k. But because these two commute, this one is also simultaneously the eigenstate of should be the translation operator T of A, which has another eigenvalue of lambda. So you know that if you make this periodic boundary condition, like if you make n times of A translation, then you come back to the origin, so-called periodic boundary condition. Then this then you're repeating this n times, means lambda to the power of n supposed to be the same as the original one, so which is this it should be 1. So that actually ends up with this lambda should be unimodular, the modulo of 1, or with some phase, which is this Ka can be 1 of some number divided by n. Okay, so that's a very simple, very fast way of saying that all the eigenstate of periodic Hamiltonian should satisfy with this translation phase and this eigenvalue. But of course, this is just single state case. But if you have an n-fold bands, like for example, transition metal, d electron can have 5 orbitals. So if this 5 orbital may not go spread all different directions, but they should stay in the same. So, but they tends to mix up depending on the situation. So in that case, we can actually make this unitary transformation of such state with this n-fold state within a tag. So now the thing is, so we come back to this K business that we discussed. So now we want to talk about, like, since we have a growth state with a translation property that depends on K, right? This translation, the eigenvalue of the translation operator takes into the IKA. So this K is actually K is a parameter. A is the position operator, but in this case you are actually translating momentum by K. Because you take you know what I mean. It's a position operator in this sense is actually making translation in momentum space. So if I actually move this growth state, original eigenstate of the Hamiltonian, and translate in momentum space by K. So we are actually moving backward to the original one. So this is actually a sort of way of removing fast oscillating term that we described. So we try to make U and K, which is actually going backward, in such way, then every translation, this will create this extra phase of e to the IKA, but it's compensated by e to the minus IKA. So UK will remain constant, robust, no change at all. So this should be translation invariant. So every UK with a translation of A should be same as the original one, and so on. So this is the condition they have to satisfy. But we move our Hilbert space, it translated by a momentum K. This K is actually sort of a parameter that we can actually move. Just like when you this in a rotating frame, we can change our in a rotating frame too, right? We can rotate, then we have a slow motion. Only slow motion remains. The same as that sense that so that we can also move our Hamiltonian, the back transform to K space, like same as we translate this by the momentum K. But in this case, we have one thing just we need to sacrifice one just by momentum P changes its position, the reference point by the momentum K, because we translated that by the momentum K. But this position periodic potential is not affected at all. So this is the so-called parameterized Hamiltonian by K. Then we have a Hamiltonian equation by this shifted K space Hamiltonian and shifted basis step, which is a periodic. So this one makes our Hilbert space and Hamiltonian all well defined. Now, the one thing to note is that once we do this, in Prof theorem by itself, if we have an nk and k prime, then they are orthogonal once if they are different. K and k prime is different. Everything is orthogonal. But also, for given k, you can have many n-fold degeneracy. With that, we can actually resolve by making unitary transformation. They can be orthogonal too. So this is always orthogonal. But now, when we discuss this like that, for given k, the same k, n and n can be orthogonal. But for this matter, we don't know about the normalization of u and k, and same n but with different k prime. So that's actually a very important point. So we are saying that in band structure like that, we are having at k point, at k, some k, we have state like here. If you take another k like this, then you have two states on the side. These k states over here and states over here, they are in fact total independent. If you take the Boole wave function, they're orthogonal. But if you move back to this k parameterized k space, then they may not be orthogonal as it's supposed to be. So with the infinitesimal change of k to k prime, there is some change. And that actually is converted in terms of this geometric interpretation. We take this as a distance in k space and so on between these two states. But yeah, we don't have time to discuss any of those mathematics. But this is the essence of that. But still, previously, the management discussed in GW a method that we deal with some wave function subspace as identity like that. But that's actually, you can translate as some projection operator, which is a subset of identity operator. And in that case, this flow state and this U and K, this periodic, the K space eigenstate, they actually span the same Hilbert space. So we can actually have that. So once we come back to this one, then now here this Vannier function takes a role. So this is a Boole state, and if you make this unitary transformation of that, which is simply summing up all this. If you just look at this one, if you take the r as 0 or whatever, here, if you take the r to 0, if you take the r to 0, you just integrate this Boole function over the k space, then you end up with some function which is independent of k. But that one, hopefully, if you optimize it well, then they can be localized within some finite size of distance. So if this calculation would original Boole state, the psi k, it might have this fast oscillation with this phase, is just taking the real part of the wave function. You have a slow varying k, but also you have a fast varying wave function node like that. But if you sum them up, then you get some localized wave function like this. And actually, same as this growth function, this u, this periodic basis u and k, in fact, has the same property as the growth function. So just for semantics. But the thing is, once you have this binary function, because once you construct this the localized binary function, then this is well, just if you can vision that as a simple localized basis in type binding Hamiltonian. So in terms of this binary function, you can construct this Hamiltonian matrix like that. To construct this one, you need to know the below function in all of different case space. But once you construct that one, then the later on is any Hamiltonian as a function of k can be actually constructed by this binary function. This is what we need actually. We need some Hamiltonian as a function of k. That's a parameter that we can control. That we can choose arbitrary k within the Bernoulli. So let's say the initial construction of binary function, we calculate wave function in DFT with finite grid like that. But once we constructed this binary function with some approximation, of course, or the best approximation that we can make, then later on, for any k with any precision, we can actually generate all the Hamiltonian with continuous variation of k. So, for example, if you have a Fermi surface, for example, it goes like this one, it's really difficult to capture all of these points from realistic DFT calculation. But once you have this way to do this, then we can control k precisely enough to control all of the points along this the Fermi surface or whatever point that you like to do. So the advantage of having binary function is to construct Hamiltonian as well as the wave function as much as precise as we want. Okay. So once we do this, then we can deal with all of this. So let me go. Yeah. So then what's the advantage and what's the physics behind all this? So we'll take the simple example that discussed by Professor Vanderbilt for many years, that he is making very good lectures on this one. So in fact, there is the Berry phase that we guessed. How many? 10 minutes. So I couldn't get to the point that I wished to, but okay, let me try as much as possible. Okay, so the Berry phase and glow state. This is two different thing, but you can vision like this way. The glow state actually provided the K space, parameterized Hamiltonian, and the Hilbert space of the wave function, the periodic wave function in K space. So that K can be treated as a slow variable that actually give rise to some Berry phase that we want to deal with. So how this Berry phase has to do with the physics that we like to discuss. I mentioned in earlier I took two examples. One is this magnetic monopole, which is obvious and very clear to understand. But other than that, there is not easy to, not a simple thing to visualize. But this is but still the electric polarization is actually very good example of visualizing the role of this Berry phase. And I think it's many experts here knows as granted, or it knows so well. But let me just describe a little bit for students to understand. So this is P is a polarization. Just ignore lambda at the moment. And if you take the P, then the polarization is the electric dipole. That means R is the position of the electron, and E is the electron charge. So suppose you are in a uniform background, so you don't care anything on the positive ion in the system, then this is the polarization you calculate. E times R, that's a dipole moment. and you then it's an expectation value of that with respect to all the occupied state, the phi sub I. So this I is the general quantum number for all the occupied states. So you calculate this and sum it up, then you get this polarization. But it's well defined for the molecule or some isolated system where you can take your reference clearly without any ambiguity. But in a periodic system, then there is a trouble. For example, look here. So you have a system like this periodistic goes this yellowish ball. This is periodic system like this. But you take your unit cell. If you take unit cell like this, or you can take the unit cell like that. It doesn't matter because everything is periodic. But if you take the unit cell like this, then if you calculate this P only within this unit cell, then your polarization is going from the center of the electron charge here to positive ion in the system. So this is the polarization over here. But you do the same calculation of this one, this quantum mechanical definition of polarization for this unit cell, then your polarization has got reversed. You point into this direction, or if you take something just in the middle, then you either way you can take the minus and plus or add it together. Then you got, if you take your unit cell somewhere in the middle, then you got 0. So it's very ambiguous, and it's hard to catch now how you define this polarization correctly. And it's even for this small unit cell, it's like that. But if you go to, if you know that you are dealing with periodic system and your eigenstate is a periodic function like flow state, which extends all of the real space, then it's actually formidable to how you calculate this, because you can take this your reference at any point. So this is another so-called ill-defined the function, and we need to. There actually some way that we can calculate this. So to do this, suppose that you have some in your Hamiltonian, there is some potential, external potential or ionic potential that actually distorts your electron. So that you take that as a V, as the external potential. That lambda is some of the position of atoms that actually break that inversion symmetry. And then by moving this atom slowly from symmetric position to the broken symmetry position, we can actually change diabatically with by changing lambda from 0 to 1. But by doing that, actually this lambda is kind of slow variable, and and also in the Hamiltonian, it also has a slow variable embedded in the potential V. So suppose this one, the position R has no lambda dependence. So this phi and this phi carries this lambda dependence. So if you take derivative of P with respect to lambda, then you have to take the derivative of this one and plus derivative of that one. But that's actually pretty not simple, but so I just wrote here to remind myself, because I also got very confused. So this is the objective we need to calculate. And then actually by Feynman-Hellman theorem, that this is actually associated with this one, change of the V. So by plugging this in here with this derivative of either side by that, we got this form. And then we can calculate this the expectation value of R with respect to these two different wave functions. Then we can use this some manipulation formula that actually end up with some of this product of these two wave function. The one side is the derivative with just the K, which is we know that we can deal with a K parameterized space. And this lambda is something that we can actually control in certain direction. So this is the way that we actually define this polarization, derivative of polarization with respect to lambda. But the interesting thing is that once we do this, then this term on the right hand side is you say that same product of these two periodic wave function with respect to Ka and lambda. So if you take K and lambda to different orthogonal slow variable space, then this is something like taking a curl of this derivative product, so which is actually end up with this very flux, the curvature of the system. So the thing is, by integrating over this lambda, we get this polarization by that. But still, this term is the integration of that as a gamma, which is a very flux phase. This is the same gamma that we defined earlier in the beginning. This slow extra phase we gained by the slow variable of that. So that's very abstract. But if you look at this, the distortion of atom and also that's associated K space, the K parameter, the variable, then you see clearly the meaning of this gamma, which is very phase by rotating and full circle, and that's actually the representation of this polarization, which is defined by modulo of 2 pi. So it can be any multiple of 2 pi, but that's meaningless if going beyond 2 pi. So anyway, the physics is that this very phase is actually polarization in a solid, a periodic solid. And the same thing can be actually visioned in a momentum space, which is actually a little more physical. So instead of calculating polarization like this, we can actually calculate by the integrating over the currents. In fact, in the experiment, actually, this is more suitable. That you have a system by applying some external voltage over sample, then there is a current induced over it, which actually accumulate either top or bottom. That actually results of this polarization. So this is actually more physical, and the thing is that this is very heuristic way of seeing that, and the calculation of this currents in periodic K space, that Hilbert space that we define, is that if you take the position operator in parameterized K space, it's a derivative with respect to K. That's how we define this momentum operator by position, vice versa. So if you just take this one, this integrating of the Bernoulli, but this one is simply the vector potential that we described earlier. And so if you integrate it over like certain path, then like for example in one-dimensional case, then this phi is actually defined by the calculation of this space, the overlap between K. In fact, if you take a discrete form of that, then you are actually taking a product of UK and UK plus delta K and something like that. So this slight overlap between two states with slight difference in K, and that's what it makes. So maybe I may not have much time, but what this just flash it in some way like that. So in practical way, because this space is more important, so this U1 and U2 is they are a little space between these two K point in K space. So if you take this product of all that, and then taking logarithm of that means that you are taking off that phase, the change of phase altogether. And since it's I times the phase that you're taking imaginary part of that, means we are sorting out the difference of I, the integration of K, the phase that lead to actually phi in our definition. So it's a discrete form of that, actually can be written as a continuum limit. But this is some point that we actually have to pay attention, because usual theoretical expression goes like this as a very familiar way of writing vector potential or connection like this. But in practice, in our case, in solid condensed matter, when you calculate in periodic system, we have to do this discretization. So this is usual way of doing calculation in our side, but this is a very formal way of writing this the very phase integral in continuum limits. So this is how we do. But the one thing to note is that while we do this, if we make a kind of gauge transformation of any local basis, but at any point of the K, there is a global degrees of freedom. You can change this phase vector arbitrarily, but actually it doesn't matter because when you do this, and every phase actually cancels each other. So when you come counting all of them, they just disappear. So this is sort of gauge invariant form of the results. So this very phase we calculate is actually gauge invariant, and as we do that, and all of our so-called the Berry potential, the vector potential, this is connection that we calculate, and we got a Berry phase like this. Of course, it's a nicer way of representing Berry phase. Then also we can calculate curvature, but there is a discrete version of this one which will come back later in the lecture, and then this is a very curvature or the flux that we discussed, and whatever the K space we make, we can calculate the Berry flux and everything, which will define in a system. So maybe I think I should stop here. So maybe we're ready for the more complicated thing next tomorrow. But so far, yes. So any question? Welcome.
Thank you, Professor Yu, for a very clear talk. Now, any questions, comments from the audience here?
Yeah.
Yes, please.
So, when your translational symmetry is invariant, so when it is commuting with the Hamiltonian, then you got this parametric space in terms of the crystal momentum. But if some of the translational invariant is break, then if you put some kinds of if somehow you will break the translational symmetry, then which parametric space will be explain all this stuff. And, you need to change some parametric space. So which kind of parametric space will give you all these very curvature and all these things?
I think the question is, what if you have impurities that break the translation symmetry, in which case you can't define your nice topological invariance? Right? That's your question,
Yes,
right?
yes.
Oh, I mean, in the real system that breaks that
Yeah.
translation symmetry.
Yeah.
As far as actually that brings back to our original assumption that we have defined this the eigenstate, the Hilbert space defined by this basis of this theoretical wave function. So as far as this manifold is not broken, then I think it should survive whatever perturbation you get in. The point of this diabatic translation in the earlier note, you have defined like, let's say you have 5 bands or 5 states as a single manifold, and that state, you put some external perturbation, that if the state is actually make a transition to something beyond this manifold, somewhere else, then you are in trouble. Then this all would say would not be valid. But as far as the whole states that you described remains within this manifold, then I think it's That's the reason why the topological thing would not break up. The same as you have a loop like this. You can try deform it somehow, but unless you break it, it still remains a
Can you
loop.
give any reference that somewhere people tell about this thing? And other than this crystal momentum parametric space, another parametric space where you can explain all this stuff.
Oh, you mean whether we have other parametric space that we can deal with this?
Yeah. Where a translational symmetry will work.
Yeah, I have a comment. So actually, in that case, instead of the crystal momentum, you can introduce twisted boundary condition. even in the presence of impurities. And then you can think of the twist angle as a new parameter. So, and then you can, compute the Berry phase, as a
Then
function
the
of
parametric space is not the crystal momentum space.
lambda and the twist angle.
Okay.
Yeah, so it's not necessarily just this one, but still I think the prerequisite and requirement is that you need to have a Hamiltonian and Hilbert space that goes together with given parameter, whatever. It could be Cauchy or lambda, whatever parameter you define. But your Hamiltonian needs to carry that. At the same time, your Hilbert space should remain intact within that space. As far as that, everything is just stay in the same logic as this.
Thank you. Thank you for the nice talk. In continuation to each question, when we talk about the twisted this boundary condition, could the vortex topology one talks about in superconducting structure is an example of that, where the twist angle in a vortex, and they define a topological invariant for that.
Yeah, I think So what superconducting state is not just this one, but you put an extra condition for that manifold, right? With a two-body correlation. So in that case, I think as far as within that sub-manifold, I guess, then yes, then I think everything should go together. Yeah.
Then you have showed that the polarization in a system, changing polarization to be precise, is proportional to very phase of the system. If one follows.
Right.
So is there any physical meaning, because one is a geometric property of the manifold that we have, and polarization is a quantity that we measure. So is there any physical reason why they are proportional to each other?
Actually, I was a little behind and I didn't control the time well. So, but we'll discuss about that. So you can actually consider the Barnier function in so-called high-grade Barnier function that people exercise quite a lot. So you are in, for example, in two-dimensional space. You treat one of the direction as just a real space Barnier function, but the other direction you take them as a parametric. Okay, and then you can actually visualize, how this so-called charge center is actually evolving with respect to variation of another parameter. So that's very clearly understood, and so what long time ago people actually figured this types of quantum phenomena like as a charge pumping mechanism or any time evolution of electric field effect or something like that, stock effect. But all of those things actually can be combined in just single picture, yes. So your real space version of this real space projection of this K-space effect, yes. So that's all should be consistent, yeah. So the topology that we mentioned is like the real topology of connectivity of those charge center in K. What you have originally two direction, but in one direction they are winding. So your winding number is literally it's a Chern number that we consider. So the question is that how we're going to calculate that correctly, or how we identify that in certain systems. Sometimes it can be hidden. Okay, so same as in superconductor. Superconductor has a particle symmetry and also something like that. But in certain crystal, you have certain symmetries actually has extra constraint. For example, like mirror plane or some gliding axis, something like that. If you have certain symmetry, or even time reversal symmetry is another famous example of that. Just topological insulator that quantum spinel effect is how we connect those time reversal symmetry embedded into this K space. Okay, so that will bring up on the same additional identification of those topological states. So we always have to watch. This is the basic playground we look at in the K space, parameterized K space with wave function and Hamiltonian. But once you have some symmetry operation within that, then certain part of K in the Brevon zone is connected to the another part, K, in another part of it. So it's already have some connection by that. Okay? So we have, it's not just simple Chern number, but it's kind of modified Chern number. So that we need to visualize and we need to identify how. So that's a subject of next lecture.
Thank you. So, any quick question from the?
So like in Dirac simulator, we have four-fold degeneracy at Dirac point. So how can we lift it to make it like Weyl simulator? Where we have double degeneracy at two different cones.
Okay. So far what I showed is a spinless fermion, the simple Dirac cone that has a magnetic monopole residing there. So without any considering any spin degeneracy and whatever. So the thing is then you're saying that you have extra spin degeneracy and some other comes in. So how are we going to distinguish those, right?
How can we lift that degeneracy?
Well, but just lifting the degeneracy is simple. You put external real magnetic field, then you will lift up the spin degeneracy.
So that we can do by externally, but like internally, experimentally, how can we do that? Like using spin orbit coupling or?
Yeah, we cannot control spin orbit coupling. It's already there. Yes. Of course, you can choose different material to put.
Like doping
Yeah.
or interconnection.
Yes. But we can discuss that next meeting. Yeah, next lecture.
There is a question from the online participants. Could you unmute and speak up?
Wow.
It's written.
No, it's the same theoretic. Yeah. So the question here is that I'm afraid of going back to probably question over here and whether no. Yes. The question is if this potential, whether we make this translation in momentum space, whether that one it is for single unit cell or the supercell or something. But the thing is, this is a position operator and they commute with potential. So it doesn't affect anything at all. So the potential is supposed to be original theoretic potential. So that remains. So this Hamiltonian is periodic as the original one. It was a period of 8. So the same is true for this one should be a period of 8. So this translation operator also commute with that too. So all the Hilbert space that we discussed and Hamiltonian we discussed supposed to commute with this one. So that's the essence of all the discussion that we made. Okay. I hope the answers yes.
So now let's thank Professor Yu again. We are slightly behind the schedule, but okay, let's meet again here at 2 p.m.
All right.